Hello and welcome to our coverage of Chapter 2 on atomic structure. So, we introduced the concept of atoms, the fundamental building blocks of matter, in the previous chapter. And I want to go into a little bit about the history of this because humans have theorized about the existence of something like atoms for thousands of years. The ancient Greeks were the ones who intuited that matter must consist of fundamental, irreducible building blocks. And it was only much later in 1808, as we saw, that John Dalton, a former British school teacher turned scientist, published his atomic theory. It wasn't really until the last century, the 20th century, that we arrived at a decent definition of atomic structure, particularly the electronic structure of the atom. So we learned in the previous chapter that J.J. Thomson discovered the electron with his cathode ray tube experiment around 1900. And then subsequent efforts to really understand electrons, electronic phenomena, catalyzed an absolute revolution in physical science by many of the scientists shown in this photo. So this is a 1927 photo from the Fifth Solvay Conference on Electrons and Photons. And this is a really famous photo because it has lots of the scientists who were the founders of quantum mechanics, which was really a new branch of physics. Of course, we have some famous faces here, notably Albert Einstein, and the only female in this photo is Marie Curie, just a little bit to his right. We also have a lot of other big names that you're going to hear over the course of this chapter. So you can kind of see the key here. We have Einstein and Marie Curie, but we also have a lot of other big names. And one that we're going to talk about in this chapter is Max Planck, who is here to the right of Madame Curie. We are also going to talk about Erwin Schrödinger and his wave mechanics theory. And who else? De Broglie is behind Einstein a little bit over here. Okay, so we have, and then the Pauli exclusion principle as well. So Pauli is over here. Or maybe this one. All right, so we have a lot of famous faces here who are the scientists who really pioneered the field of quantum mechanics. So everything we're going to talk about in this chapter kind of comes about from their discoveries in the very early 20th century. Today, we're going to talk about light energy and what it reveals about atomic structure. So light energy is really important. And when we think about light, we can use light and energy synonymously. We can think about it as having both wave and particle-like properties. Okay, so light, when you think about it, and we're going to talk about it as a wave first, but we'll also talk about it in the form of particles. Light has wave motion properties, so traveling in a wave, for example, having a wavelength. We're going to define what wavelength is in just a second. And it also has particle-like properties. It exists as photons. Photons are just light particles. So this wave-particle duality is extremely important, and you really can't fully describe light energy without considering it as both wave and a particle. So I want to talk about the wave properties first. Let's see, the wave properties of light first. And here I've drawn two different waves that look just like squiggles. And I want to kind of define the axis here. Just going to give you an arbitrary number. Oh, that's not very straight here. Let me make that a little bit prettier so we can actually try to see. I think that's even worse. Okay, but you get the idea. This is just a metric. I want to tell you that this length, I'm going to arbitrarily define it as 1.6 times 10 to the minus 3 meters. I'm going to call this wave A. This other squiggle below it, I'm going to call it wave B. So I want you to notice a couple of things about these two waves. First of all, I've drawn this on graph paper here. We have this kind of height here. This distance between the trough and the crest of the wave, we could say it for either of these, this would be defined as the amplitude of the wave. You could think about the amplitude as just the height from the crest to the trough. There's another very important distance that I want to define today, and that distance is the distance between trough to trough or crest to crest. These should be identical, and what those distances are wavelength for that particular wave. Okay, so if you measure, you can take a measurement from the crest to the crest or the trough to the trough, doesn't matter, you get what's called a wavelength. And the wavelength is the same regardless of where you choose to measure it. We abbreviate wavelength with a lowercase Greek letter lambda. Okay, so the lambda values for that first wave, wave A, are kind of marked up there. Let's look at the second wave, wave B. Here, if I measure from crest to crest, that's going to be my lambda, or from trough to trough, that would be my lambda. So each of these waves, wave A and wave B, has its own unique wavelength. Okay, so we can also define another parameter, which is frequency of a wave. So any wave is going to have a frequency. Frequency is denoted with this lowercase Greek letter nu. Nu kind of looks like a cursive V. But the frequency, as its name implies, is really the number of wavelengths that pass a given point per second or per unit of time, but usually we measure it per second. So if you look at this first wave, wave A, you can see it has a certain frequency. Wave B has a higher frequency. You can kind of see that by just the fact that you're going to have more wavelengths pass a given point per second if they're going at the same speed. And indeed, light is always going at the same speed. It's going at the speed of light. So imagine if we take the wavelength and multiply it by the frequency, that's like saying distance multiplied by the reciprocal of time, right? Because wavelength is measured in distance, frequency is measured in per seconds or per time. Now, the distance per unit time, of course, is something you may have heard of before, the speed or velocity. I'm going to denote that with a V for velocity. However, this velocity is very special. If we're talking about light energy, specifically, we are talking about a very special velocity called the speed of light. And instead of a V, I am going to call that a C, because it's a constant, the speed of light. So we can define this very important equation, which is that the speed of light is equal to the wavelength of light times the frequency of the light. Speed of light in a vacuum is a constant. It always has the same number, something you can look up. It's 3 times 10 to the 8th meters per second. It's quite fast, right? But you can imagine that the speed of light in a vacuum is going to be pretty fast. This is a very important equation because since the speed of light is a constant, if we have the wavelength, we can get the frequency and vice versa. So let's go back to wave A and wave B for a second. Looking at wave A and wave B, which wave, A or B, has a longer wavelength? Okay, so as I've drawn them, this kind of distance at the top here is 1.6 times 10 to the minus 3 meters, and it applies to both of them. Just by eyeballing it, you can see that wave A has the longer wavelength, right? And this equation shows us that wavelength and frequency are inversely correlated, right? Since when I multiply them, I get a constant. They must be inversely correlated. That means that the longer the wavelength, the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. Okay, they are inversely correlated. So we can actually quantify this. The wavelength of wave A is going to be, well, we had 1.6 times 10 to the minus 3 meters total, but that encompassed, let's see, how many wavelengths here? 1, 2, 3, 4 wavelengths were kind of encompassed in that 1.6 times 10 to the minus 3 meters. So that means that I can calculate the wavelength by dividing that total distance by the 4 wavelengths that it encompasses. So that's going to give me a wavelength of 4 times 10 to the minus 4 meters. Similarly, the wavelength of wave B is going to be 1.6 times 10 to the minus 3 meters divided by, well, let's look at it. In that distance, we have 1, 2, 3, 4, 5, 6, 7, 8 wavelengths encompassed. So I would have to divide that number by 8 to get the wavelength for wave B. So now we have a quantitative proof that A has the longer wavelength, which is what we kind of saw just by eyeballing it. So this is going to be double the wavelength of wave B. Now, which wave has a higher frequency, wave A or wave B? Well, just by looking at wave B, we can see that more wavelengths are going to pass a given point per second, given that both of these would be traveling at the speed of light. And we can actually quantify that by using the equation that relates wavelength and frequency to the speed of light. So the speed of light is wavelength times frequency. The units of wavelength are always going to be a unit of length. Usually it's some form of a meter, so nanometer or picometer, something like that. Frequency is going to be measured in units of per second, or 1 over a second. Sometimes you see that expressed as seconds to the negative 1, or what's called hertz. Hertz is abbreviated with an HZ. 1 hertz is 1 per second. So that means sometimes you'll see megahertz. 1 megahertz is equal to 1,000,000 seconds to the negative 1. Okay, so you might have seen that. Megahertz is what the FM radio waves are measured in. All right, so let's calculate the frequency of wave A and the frequency of wave B. The frequency of wave A is going to be the speed of light divided by the wavelength of wave A. Speed of light is a constant, 3 times 10 to the 8th meters per second. The wavelength we just calculated is 4 times 10 to the minus 4 meters. So the frequency of wave A is going to be equal to 7.5 times 10 to the 11 hertz, or reciprocal seconds. The frequency of wave B we can calculate in the exact same way, just using the wavelength that we calculated for wave B. So that's 3 times 10 to the 8th meter per second divided by 2 times 10 to the minus 4 meters. That was the wavelength that we calculated for wave B. So that comes out to be 1.5 times 10 to the 12 hertz. So which wave has a higher frequency? Indeed, we see that wave B, as we predicted, has the higher frequency of these two waves. So wavelength and frequency are inversely correlated.